Well, thank you very much for inviting me here and giving me the opportunity to kick off this workshop. It seems to be as though we want to start with a bit of a blast from the past. So I'll be saying something about why I got interested in mechanism design in the first place, though it also relates to where I'm planning to go. So, mechanism design in public economics, and actually this is the first part of my abstract, which I just put there. Lusin's theorem, a measurable function, can be approximated by functions that are continuous except on arbitrarily small subsets. We'll consider mechanisms where a principle is confronted by a continuum of agents, which is a case which has been used by many researchers to discuss problems in public finance. And I guess Roger Guénory's Econometric Society monograph, Contribution to the Pure Theory of Taxation, has much in common with what I'll be discussing here. And the Vickery Murli's model of income taxation arises when workers have varying skills, and it illustrates why one should allow non-measurable mappings from a unit interval to agents' hidden types. Working with Yaning over the years, we've had many discussions of issues of this kind, but now I can say non-measurability is actually something we need for problems to be interesting. Otherwise, we'll get some relatively trivial answers. So let's start with, welfare economics, probably a good idea always to start with Kenneth Arrow. And especially his extension of the basic theorems of classical welfare economics, what I like to call the efficiency theorems, linking perfectly competitive markets to Pareto efficient allocations and welfare optimal allocations. And the second efficiency theorem says that under convexity and other conditions, any Pareto efficient allocation which is non-oligarchic, if I had more time I'd explain what that means, basically means not extreme. You've got to stay away from various edges of a relevant simplex, can be achieved through perfectly competitive markets with appropriate lump sum wealth redistribution. So the maximum of any Paretian Bergson-Samuelson welfare function can be reached through markets, but only if you have appropriate lump sum wealth redistribution. And again, relative to a status quo allocation, you can have Pareto gains from expanding the scope of competitive markets, but only in general with appropriate lump sum compensation of those who would otherwise lose. So lump sum redistribution plays an important role in getting to a welfare optimum or in distributing the gains from trade. Now, what about the information that you need to have appropriate lump sum redistribution? Well, Samuelson, in his PhD thesis, Foundations of Economic Analysis, pointed out that arranging suitable lump sum compensation to those who would lose from market expansion requires information about economic agents, especially their true needs and capabilities, and there are practical difficulties in encouraging agents to report these truthfully. And some of the issues came up in his versions of the gains from international trade, the theorems he had. And he also, a related problem in the discussion of public goods, looked at the free rider problem, that people don't want to acknowledge that they're willing to pay for public goods. They want to understate their willingness to pay because that typically means that they actually are asked to contribute less. Now, Leo Hurwitz, of course, really introduced us to the modern theory of incentives. Well, I'm going to mention Vickery as a precursor, but Leo was really important, and of course, co-winner of a Nobel Prize for this line of work. And his main contribution, I think, was to say that one should study mechanism design by seeing what emerges from equilibrium in a well-chosen game form. You want to design something like a market mechanism or another mechanism, which in Hurwitz's work you model as a device of a game form, and you want the equilibria to be at least Pareto efficient. I want them to be more than Pareto efficient because I'm concerned with the redistribution of income as well, to avoid extremes of poverty and to ensure gains from trade and so on. He also considers strategy-proofness. He introduced a definition of a strategy-proof mechanism as a game form in which truthful reporting of one's true type is a dominant strategy. By the way, that's already there in Vickery's work on the second price auction, but Hurwitz was doing it for general economic systems. And he had a particular result that in an Edgeworth box economy, 2 goods and 2 agents, any strategy-proof mechanism that achieves Pareto-efficient allocations must be dictatorial, give all the goods to one of the people. And that suggests that a Valrasian mechanism could be Leo suggested that a Valrasian mechanism could be strategy-proof if you move to a world with infinitely many agents. And it was that insight, I think, that led me to start working on strategy-proof mechanisms with a continuum of agents in the 70s. Of course, Gibbard and Satterthwaite had their famous impossibility theorems on strategy-proofness, but that's with a small number of agents. Doesn't apply when you have many. And the lesson I take from Gibbard, Satterthwaite, and Hurwitz is don't bother looking for strategy-proof mechanisms when there are finitely many agents. They can only be found in extremely rare circumstances. For one case, which has not generally been looked at, revolves around what used to be called the non-substitution theorem. There are economic environments where technology, constant returns to scale, no joint production, only one scarce factor, determines that even with a small number of consumers, prices are determined entirely by supply independent of demand. And so in that kind of setting, what consumers reveal about their demands and their willingness to pay for different goods has no influence on market clearing prices. So then you will have a dominant strategy mechanism. But that's a very special case. So generally we consider a continuum of agents, useful in discussing public design, mechanism design in the context of public economics. So now let me come to the Vickery-Murli's model, which is a prime example of what can go wrong if you try and implement the first best. So Vickery, in this remarkable paper in 1945, amongst others, discussed measures of marginal utility and original position, and also formulated the optimal income tax problem, which Murli's discussed and really solved later. Vickery just said there's a calculus of variations problem and discussed Euler-Lagrange first-order conditions. Murli's found numerical solutions. So here's the problem. How much to pay workers of different skills, and you want to achieve fairness while presumably preserving incentives. So N denotes a person's skill level, and it's defined so that a worker's productivity is proportional to N. So N is a measure of productivity. And the distribution of workers' skills, it is a continuous density function. This is an assumption of both Vickery and Murli. So we must be into really a continuum of agents as an idealization. We have a continuous distribution of skill levels. So this is a simplified case. We'll have a representative consumer worker whose preferences for consumption and labor supply pairs C and L. It's the utility of consumption, U of C, minus the disutility of labor, V of L. And we'll have U be strictly concave and V be strictly convex. And the social objective is to maximize the utility integral, the mean measure of utility in the population, by choosing consumption and labor supply for each individual as functions of their skill. And there's a resource balance constraint that says mean consumption can't exceed W, some measure of productivity, times mean effective labor supply. So you've got L is the integral, you've got N here. You multiply the labor by the skill level, right? So someone who's twice as skilled, each hour of their labor produces twice as much output. So it's mean effective labor supply, which could be distributed as consumption. So here's a first best. Let's consider, at least formally, Lagrangian functional, which is the utility integral on the first line, minus lambda times, this is the constraint that says mean consumption can't exceed W times mean effective labor supply. And this is non-rigorous, but supposing we differentiate the integrand, pretending that derivatives both exist, then you get what I'm calling pseudo first-order conditions. So 0 is the derivative of the Lagrangian with respect to C of n, holding other things fixed. Of course, if you just vary C for one value of n, it has no influence. But anyway, if we differentiate the integrand in the right way, we get the marginal utility of income for the n person minus the Lagrange multiplier times the density. And when you differentiate with respect to the labor supply, it's minus the marginal disutility times the density plus lambda Wn FFN. So if you solve these two first order conditions, so this one says that marginal utility should be lambda for all individuals, so C should be the same for all skill levels. And this one, well, if you differentiate it, then the marginal disutility of labor is lambda times Wn, and if you differentiate that with respect to n, you see that labor should be a differentiable increasing function of the labor supply. So Marx wrote from each according to their ability to each according to their need. So this first condition seems to be to each according to their need. And this is from each according to their ability in the sense that the more able are expected to work harder. So you can prove that these first order conditions are sufficient. This is a bit like the Magnusarian proof of sufficient conditions in optimal control theory. Similar idea. If you satisfy the two first order conditions, and if you look at any other policy involving consumption and labor supply as a function of n, satisfying the resource balance constraint, then the mean utility here is less than or equal to the mean utility on the presumed optimum, where everybody gets the same level of consumption and the labor supply solves this first order condition. So that's the claim. And, well, it's really extremely easy to prove, just using the fact that the concave function at gradient is a supergradient. So a tangent to any concave function lies above the graph, and the tangent to any convex function lies below the graph. So if you use the supergradient and the subgradient properties and integrate, it's all very straightforward. Okay? And you get optimality. Well, that was Marx. I discovered actually from a colleague who was giving a lecture on the centenary of the Russian Revolution, somebody who works on Soviet economic history, that already by 1917, Lenin was saying to each according to their contribution rather than to each according to their need. And the incentives, obviously, if you're going to have the more skilled work harder but pay them no more, then you're going to encourage a society where everybody pretends to be stupid. It doesn't work too well. So income taxation, a worker who supplies ln hours of labor, the effective labor supplies ln times ln, and if they get paid their wage before tax, then their labor income is Wn times L. And so the optimal taxation literature, you subject this income to a nonlinear tax function, so y T of Y is the tax you have to pay if you earn Y. And things like earned income tax credits, this could actually be negative in some cases. So after tax income, which equals the person's consumption, C is Y minus the tax, and the marginal rate of tax is T prime Y. And provided the marginal rate is less than 1, then those who increase their supply of effective labor will be paid more net of tax. So at least you have those weak incentives preserved. So the Vickery's Murli's problem was to choose the tax function to maximize the same integral, subject to the resource balance constraint, but also a decentralization constraint. Each consumer or worker chooses optimally from a budget constraint determined by the tax function. So as functions of N, their skill, they choose C and L to maximize utility of consumption minus disutility of labor, given the tax schedule. There's an alternative solution that Partha Dasgupta and I came up with in the late 70s, published in 1980, which was if you could observe work effort as well as income, then you can base taxes on the revealed skill directly. And so we were able to get an allocation where consumption and labor supply both increase with skill, but everybody has the same utility. And that's actually a sort of Rawlsian allocation. It maximizes the minimum utility, the utility of, well, everybody gets the same utility subject to the resource balance constraint. And that's just a remark. Okay, well, with these results in the background, perhaps, we then started to think about mechanism design with many agents. And, I mean, Horowitz already encouraged to think that a competitive market mechanism will work well in his sense of being strategy-proof as long as you have lots of people, and so they have no influence on market prices. Lots of literature. So let's now think a little bit more formally about mechanism design with many agents. So in the 70s and 80s, I took an important shortcut, as I now realize, which was to consider just the distribution rather than the labels of agents. But formally, the modern literature on mechanism design typically treats the problem as a game of incomplete information. And so in due course, perhaps we should align our work with that by looking at games of incomplete information with a continuum of agents. I've done a little work along those lines, but haven't got so far. Now, unlike Yaning, I like to work with a Lebesgue unit interval. I feel what integrals, I feel I know what integrals mean in such a setting and can do the integration. Maybe. So anyway, there's the Lebesgue unit interval. And observable labels, because we're going to base things on the labels. And the characteristics of agents, which in the Vickery Murli's model was simply their skill, but in other contexts can be much richer, of course, will live in a complete separable metric space. Agents' hidden types, their preferences, their skills, even in some contexts, their endowments and so on, production possibilities. And so we can assume that there's a joint distribution of pairs, labels, and types on a probability measure nu on the product of the two. And of course, the distribution of labels is lambda, so lambda should be the marginal on L of a distribution nu on L cross theta. So this last thing, set of measures on L cross theta whose marginal is on L is lambda. Actually, this may not be the best notation. I think I used a different one in a recent paper, but it's the one I'm going to stick with today. And we're allocating goods, finite set, commodity space. And we'll be interested in net trade vectors. Not necessarily consumption vectors, because consumption includes endowment, domestic production, and so on, which may not be observable or directly controllable. It's the net trade vector which represents how any agent in an exchange economy interacts with the rest of the economy. And we'll assume that a hidden type determines a closed feasible set with no trade as an option, and complete and transitive preference ordering on the feasible set. And an allocation mechanism, you take triples consisting of a label for an agent, an unknown type or characteristic of the agent, and this joint distribution of pairs I theta, and map it into a net trade vector, and F will be the function I'm looking at. So net trade vector is a function of those three things, and it's resource balance in case the mean net trade vector is 0. By the way, there's a presumption here that you can integrate the mean net trade vector, so it better be a measurable function. We may have to come back to that. But we'll look at resource balance mechanisms. Lebesgue unity interval was atomless, and the marginal of L of nu, I've missed a symbol here, there should be a nu here. The measure nu can also be seen to be atomless. This is useful because if you think of an agent whose true type is theta and pretends instead to be eta, then instead of the triple I, theta, and nu, it looks as though this agent, the relevant arguments in the of a function determining this agent's allocation become I, eta, and nu. But it's the same nu because if only one agent changes their type or characteristic, this has no effect on the atomless measure. So strategy proofness means that for every triple I, theta, and nu, and every alternative eta, provided Fi, eta, nu is feasible, the outcome of telling the truth with a theta there is weakly preferred to what happens if you tell eta as well. And this is the same theta here and here, tells you that its truth-telling is an optimal strategy. Now you may wonder, well, what happens if they announce an eta where the mechanism gives them something which is not feasible? Well, that's part 2 here. If it's not feasible, if it doesn't belong to the true feasible set, then presumably something's going to break down. The agent won't be able to deliver the goods as supposed to, something of this kind. And so we assume that the mechanism breaks down in an observable way, and we can punish the agent by giving them the net trade vector 0. Maybe I should model that more explicitly. And in another paper on 22 steps to Walrasian equilibrium, that's exactly what I did. And of course, the first part just says that if it is feasible, then the agent is no better off by misreporting their characteristic. Okay? That's the strategy proof mechanism in this context. And there's a simple decentralization theorem that says that the resource balance mechanism is strategy proof if and only if there's a budget decentralization rule, or Vickery would call it a taxation scheme. So that for every pair consisting of the agent's label and nu a distribution. By the way, in much of the earlier work, I ignored the I. Everything just depended on nu. Everything was treated symmetrically, but B now depends on I as well as nu. And so the agent, basically, what this says is that the agent's allocation under the strategy proof mechanism will be one that maximizes their preference ordering over the budget set intersected with their feasible set. So agents are being asked to maximize preferences over a budget set just as they are in Valrasian equilibrium. But here, instead of a Valrasian budget set, we've got a general nonlinear budget set, perhaps, as in the optimal tax mechanisms, and many variations. So the budget set reflects an agent's trading opportunities after tax. Proof is pretty easy too. If you have a decentralization, then if a theta agent pretends to be an eta agent instead, they must still be in the feasible set. Well, if it's still in the feasible set, the definition of decentralization says that you must still be in the budget set, right? You can only move to points within the budget set. So if you pretend to be an eta person rather than a theta person, you will get something that maximizes the preferences of an eta person over the same budget set. So you'll be in the same budget set, BI new. And so that just ensures that what the eta person gets, which maximizes their theta preference ordering, can't be dispreferred to what an eta person will get. They'll just move somewhere else in the same budget set. Can't do better. As for the necessity of a decentralization, if a mechanism strategy proof, just construct the budget set as the range of the mapping, the set of all possible net trade vectors that the agent can get by pretending to be someone else. This construction implies that if X, any net trade vector in the budget set, there's a characteristic, eta, such that X is what's allocated to the eta person, given I and U, and provided this is feasible, strategy proofness implies that then Fi theta nu is weakly preferred to this X. So the budget set we've constructed is a decentralization. Okay, simple enough proof to get on one slide. Now, I'm going to look at some degenerate mechanisms. Now we're going to lead up to the use of Lusin's theorem. That should be just enough time, I hope. And so this would be where the mapping, so here we've got labels, and here we've got types. So maybe you know you've got a continuous function, or eventually a measurable function. So in some ways, the mechanisms so far have looked at all possible combinations of a label and a characteristic. But if you know that you've got a continuous function, then many of the pairs are irrelevant. Anyway, given the set of agents' numerical labels and their types, let theta superscript L denote a typical mapping whose graph I've given in this diagram, graph gamma. And there'd be three spaces. One is when we have all functions, three cases. Second case, measurable functions. And the third case, continuous functions. Now, if we know we've got a function, then the joint distribution of pairs theta and I, which should be I really, I in L, is going to be degenerate, right? It's going to all be along this curve. So we'll attach measure nu to the graph. And actually, if this joint distribution is supported by the function in this way, then the measure of any set, so you think about the set of points on this stretch, drop these two vertical lines, and it's just going to be the Lebesgue measure of this interval. Those are the only news that you're going to be concerned with. All right, so here's the result. So let's think of the Vickery-Murli's model. And of course, you don't really want this, but we're saying, okay, incentive constraints prevent us reaching from each according to their ability to each according to their need, right? The incentive constraints avoided that. Well, but if you can label persons with numerically, and if you happen to have a continuous function going from their labels to their skills, then we'll be able to do something different. The incentive constraints will have effectively no bite. So let's think about a target mechanism like the first best in the Vickery-Murli's formulation and see if we can't reach it. So we'll be interested in trying to achieve a target mechanism which for each distribution satisfies the resource balance constraint. Target has a star. So an obvious target in the Vickery-Murli's model. That mechanism is not strategy proof, right? But we may be able to modify it so that it is. So we're going to construct a mechanism F which equals F star along the graph, the support of this distribution, and can be anything elsewhere, and will be strategy proof. Okay, so we look for a strategy proof mechanism which matches the target when you're in the graph, but can be something else off the graph. Okay, so actually what I wrote there applied in general, but now let's think about the continuous case where we have a continuous function supporting things. Given any target mechanism on the restricted domain of continuous distribution supported by a continuous function, the claim is there is a strategy proof mechanism which is the same as the target when we look at I's actual type given this curve. I's actual type is the same, and that's for almost every pairs along this curve. Okay? So in other words, along the graph of things that matter, we reach the target. All we've done is specify things off the curve so that things work. And here's what we do. So the distribution is supported by a continuous curve. And what we're going to do, for any agent here, any agent will ignore what they say, will only look at the limit of what their neighbors say. And given continuity, that's going to work well and reach the target mechanism and be strategy proof. That's the idea. Works in the Vickery-Murli's model. Well, that's in the continuous case, but what about measurable case? Well, here's where Lusin's theorem comes in. Lusin's theorem says if you have a measurable function, then for every epsilon, no matter how small, you have an exceptional set whose measure is less than epsilon, such that the restriction of phi to the complement of L epsilon, the non-exceptional set, that the restriction of a function is continuous when you give this subset the relative topology. Now, a classical case would be of a function which is measurable but not continuous is, I guess, a step function where you say, okay, for any rational number, the function will be 1. For any irrational function number, the function will be 0. Well, that's very discontinuous. But if you remove all the rational numbers, set of measure 0, and just look at the irrational numbers, then you get a function which is 0, and so continuous on the relative to the domain. Okay? So you bring back continuity. Well, you can't do it that simply generally. This is the best you can do. But here's what we now have. target mechanism on the restricted domain of distribution supported by a measurable function. Then for every distribution you have an exceptional set, measure less than epsilon, and a strategy-proof restricted mechanism. So you exclude the points of the exceptional set and look at the rest, and you get essentially the result we had before. So if you really had measurable mappings from labels to types, you could get arbitrarily close to any feasible mechanisms. Incentive constraints would have no bite, and we wouldn't be here. Okay, time is nearly up. I'll forget about the proof. Random processes. Yaneng and I have looked at processes that do yield non-measurable sample paths. Some time ago, on top of a Borel measured set. That's what the sign says. So it really is measured, not far from Stanford in California. We were able to define a random process, look at one-way and two-way Fubini extensions, but I guess we don't really have time for that. So, when we have a Lebesgue unit interval, a two-way Fubini extension, which does give you nice measurable sample paths, exists only in degenerate cases. So we need to focus on one-way Fubini processes, which will typically have non-measurable paths, and then we'll have interesting incentive questions. And we can use them to model the difference. This is the second part of the abstract, which I didn't get to at all in the talk today, but this is where we should go. Processes to model hidden types, messages to the principal, allocations, and even trading on the side. Well, so many thanks to Yichun and Yaneng for arranging this and invitation. And thanks to everybody. And I guess I'm more or less finished on time. Thanks a lot.